This is the user output. First, view the distribution, literacy prediction. Okay, with biology. Yeah, wait to about because reinforcement learning. So there are two terms that we are doing. This is discussion. First, we have an agent. An agent, a learner that interacts with the environment, or a decision maker that interacts with the environment and makes decisions. Takes actions. So the environment, this is where the agent operates and takes actions. And so simply the agent operates the environment, and then when we have a state, this is how the current situation of the environment is represented. So moving on, this is action is a set of possible moves an agent can make the environment, or a set of possible decisions, possible decisions an agent can take in the environment where it's operating. Then we have a reward. This is the feedback an agent gets from the environment after interacting with it or taking action. Environment. We have a reward function. So this is a function that assesses the reward that the agent should get based on the action it has taken, state the environment was in. So we have optimal policy. So this is a strategy an agent uses to decide an action to take the environment, basically on the state of the environment. So we have expert trajectories, illustrations. So this is a sequence of state action pairs. It is the observed behavior of the agent as we have its the actions taken and the state the environment was in. So we have those pairs and we have the observed behavior of the agent. So generally, an agent takes decisions or actions in the environment based on the current state of the environment. And then, after taking that decision or making that move, the environment rewards the agent with the feedback. That's how the agent keeps on learning and getting better. So reinforcement learning is where we have an agent and it learns to make decisions by interacting with the environment or by taking actions in the environment. And in this case of reinforcement learning, the goal is to maximize the accumulated reward. So Looking at how reinforcement learning works. Here we have an agent, we have an environment. As we've said, the agent takes action, the environment. The environment rewards the agent based on this action, state environment was in. After the agent has taken an action on the environment, the environment has to give feedback to the agent and the state, the current state it is in now. As we've said, goal this technique is maximize the accumulated reward the agent. So inverse reinforcement learning. Inverse reinforcement learning is the opposite. And so, as we've said in reinforcement learning, an agent acts on the environment and uses the predefined reward function to evaluate the outcomes of its actions, which are called rewards. So, and we've said in reinforcement learning, an agent is aiming at maximizing the cumulative reward by learning optimal policy. But here, in this case of inverse reinforcement learning, the reward function, first of all, is unknown, and the goal is to use the reward function. But what do we have? We are getting this reward function. We have the expert trajectory of the observed behavior. The agent. So it's where we're trying to generate the reward function from. And as you can see, they have illustrated here. This is reinforcement learning. We have rewards, we are getting the behavior. So here, in this case, it is the opposite. So moving on to the concept of limitation. So limitation, training the model is trying to imitate the behavior. The expert. So it copies the actions performed by the experts and there's particularly no reasoning about the outcomes of the actions. But for inverse reinforcement learning, it goes beyond the concept of imitation because we find about the outcomes, actions, inverse reinforcement learning. So as we said here, we copy the intent of the experts and take different actions. So inverse reinforcement learning helps an agent to learn complex patterns of actions and specify a reward function. As I've said, in inverse reinforcement learning, unlike reinforcement learning where the reward function is predefined and it is used to evaluate the what. In this case here, the reward function is unknown. However, we only have the expert trajectory, and it is what you're using to generate the reward function. So, but there are always multiple possible reward functions, and this always causes ambiguity. So now, like in this example here, we're demonstrating, we have this orange triangle and a purple triangle. So this green ring is supposed to move. The next, here we're seeing the green ring, the green circle moves until the purple triangle. So as you have said, inverse reinforcement learning always have multiple possible reward functions. For example, in this case, we have a orange triangle. So one reward function might have been to move away from the orange triangle, and it finds itself in the purple triangle. Another reward function would have been moving rightwards, still would have found itself, would have found this green circle in the where it is in the purple triangle. Or the reward function could have even been to move towards the purple triangle. Still would have given us the same thing. So to reduce this ambiguity, this is the ambiguity we're talking about. Now we don't know the exact reward function that has led to this function. And so now to solve this ambiguity that you have seen up there, we can use a number of methods, one of which is principle of maximum entropy with inverse reinforcement learning. So we are in this case, we are maximizing the entropy, but what is entropy? Entropy is we are measuring the uncertainty. We are measuring the uncertainty of the distribution. It quantifies the randomness in a discrete probability distribution. So when we maximize it, we end up having this ambiguity, and it helps us find what function. So entropy is defined here, and then this is the equation for entropy. And this equation is summing up the product of the probability of all possible values of x and the logarithm of that probability. So probability of xk, in this case, is the probability that discrete random variable x give values. Yeah. x1, x2, up to xk. That is entropy. And what we are going to try to maximize, get rid of the ambiguity and get the real reward function. So this is the interpretation of this vision. So if all outcomes, all the probabilities are equal, for example, probability of xk is 1 out of k, the entropy is maximized. If one outcome is certain, previously this, if the entropy is maximized, it means you have high level uncertainty. That is what you're trying to get. So if one outcome is certain, for example, probability of xk is 1 for some value of k and 0 otherwise. So the entropy is 0 in this case because you're sure of what the outcome is going to be. So as you have said, higher entropy means greater uncertainty. And lower entropy means more predictability. You don't want predictability in this case. So an example of tossing a coin. For example, when you toss a coin, if you're not sure that you're going to get a head or a tail, you're very sure. In that case, you're very certain, and in that case, the entropy is 0. But when you toss a coin and you're unsure, you don't know what you're going to get, whether it's going to be a tail or head, the entropy is very high. So that's what we're trying to get. So we try to maximize the entropy in order to remove bias of the model. So now this is the maximum entropy as reinforcement learning. So we set we in the inputs for this principle, we have to get a set of expert demonstrations, trajectory. In this case, so here is a sequence of state action pairs. Need state action pairs in different demonstrations. Okay, so the state space, the state and action space. We have a feature representation, a feature representation for each state, and the transition probabilities. We also have the discount factor. So next thing you do is compute feature expectations. This is the equation for computing feature expectations from expert trajectories. Remember, I've said expert trajectories are that is a sequence. It is a sequence of state action pairs. Next thing you do is define the reward function to try to induce or infer. So in this case, W is the weight vector to be learned. Next thing you do is compute the probability of reaching a state. And then you update the value of W, which you have said is the weight vector to be learned. You update it using gradient ascent. So why use the principle maximizing entropy? As you have seen in the previous example, there are always multiple possible reward functions, as you have seen. In the other case, we had 3 possible reward functions that could explain that expert's behavior. The expert behavior in the other case was moving from orange to purple. And we saw 3 possible reward functions. So when we maximize entropy, it will reduce that ambiguity. So and then if a model becomes deterministic, it has low entropy, it may overfit the observed data, the observed behavior of the model. So now another thing is to capture the variability in expert demonstrations so that the model will be able to operate in environments where it's high level uncertainty. So let my colleague here, feature matching as another method.
I'm going to take you through feature matching. So feature matching, this is just another technique. That's reinforcement learning. So how does this work? Feature matching involves a reward function using expert demonstrations instead of imitating. So we have already seen what expert demonstrations are. What the expert trajectories. These are like the sequences of state action pairs performed by an expert. An expert is like just an agent or a model that performs actions using like an optimal policy. So we consider an expert to know what they are doing and they're performing right actions for a given state. So here in feature matching, we just want to deduce a reward function using those expert trajectories instead of imitating. So I can explain imitating. We have two forms. That's the standard and like the human. So for example, if you kind of want to deploy like an agent into the environment, let's say a robot, and you want it to perform certain actions, you could teach it or you can make it learn using imitation. First, you could hold onto its arms and show it what to do, or you could do what you want it to do and it will do it. But it will do it exactly as you do it, and it won't have any reasoning behind why you're doing that action and what you're trying to achieve. But so there's also like human imitation, whereby human is going to like always look for that intention and reason behind why you're doing certain actions, such that they could use alternative actions to achieve the same goal. So we don't want standard imitation here, but really want to achieve the human imitation that has reasoning. So this is the mathematical formulation for feature matching. And first of all, we have 3 steps to define a reward function. And we have RS. This stands for the reward at state S. We have W, which are the weights. And the weights just show the feature importance. So feature with high importance would be more prioritized over the others. T, just get the transpose. So W is going to be like a vector of that shows feature importance. And we have phi S. That is like the feature vector that represents the states. Feature vector representing states. So let's say like we have an example like of someone trying to imitate an expert Go player. So you want to achieve their speed, how they dodge openings well, and how well they score. You have those states of like the speed, the positions you're in, and so on. So the next step, you compute feature expectations. And here we have feature expectations for the expert policy and feature expectations of the land policy. So these are just like this shows the average occurrence in different feature values according to the expert demonstrations. So mu E, you're trying to find like the average scores for the expert. So where you see phi E, that is like the expert policy. And you want to sum up those using that feature vector that represents a state. So you keep on iterating plus you add from when a state is t is equal to 1, and you shall have like states S1, S2, and so on. You keep on examining. Next, we have these are like the complete feature expectations of a land policy. So I don't feel like you want to find the average occurrence of different feature values in the land policy. And phi is the policy, as we have seen. And phi S tiers, just keep on adding the different states from S1 up to T. So the last step is you match feature expectations. Because what you're trying to achieve here, you want to ensure that the expected future statistics of the land policy are similar to those in the expert policy. So you don't want to have a gap between like an agent is performing actions based on the land policy, but that policy is so different from that one of the expert. So that's why you're going to match future expectations from the land policy and match them to those ones for the expert policy, such that you have something that you have the agent doing something that is similar to what the expert was doing. So the assumption here is that the expert really knows what they are doing, and you assume that like the actions they take for a certain state are the right ones, and that means you want your model or the agent to follow the same actions. Yes, so that's mostly what feature matching is about. So this is like a small code snippet, like an implementation. This is for entropy. And it's going to show us some of the 2 steps that are crucial in like implementing these techniques, both feature matching and entropy. So one of them is you have to like define an environment, the environment where the agent is going to be operating. And the other thing is transitions. So the environment in this case, first of all, you import some libraries. We have NumPy and we have Bloxam EXP. This one is for like calculating the maximum log likelihood in entropy. Yeah. So first of all, you're going to create an environment in form of classes. You're going to use classes, and this one is a grid world. And I think a grid world is like a square, a big star, but it's more squares in it, something like that. And this one is going to be 5 by 5, the size. So you initiate the size, you have the states, you also have the actions, and then the transitions. So actions, you have 4 actions here. You have the up, you have the down, the left, and right. So that's how your agent will be moving in that grid world. So not transitions. Transitions are like movements you make like while performing these actions. Like you see moving from transitioning from up to down or from left to right. Yeah, so that's a simple explanation of the transition. So, we have a function here for build transitions. And here it creates a transition probability matrix, probability of S prime given S. So this one just helps us get a probability of an agent transitioning from state S to state S prime, given it performed action A. So we are using conditional probability. We have a variable P, and this one is just going to like it's equal to like the 3D NumPy array, which is initialized with zeros. So this NP dot zeros. Read this, so we have three like parameters. We have states, we have the action and the last state. So we have the current state, the action, and the next state. Yeah, so this for loop just helps us to iterate. It's going to like iterate over all the states. Yeah, so for S in range states, you iterate through all the states. And we have another iteration here for A. Dx, dy in enumerate, you iterate through the actions. So I think the first one, this would be like right, then left, then we have up and down. So it's in 2D form, like coordinates. So after iterating over all the actions, you're going to compute the next state, nx, ny, with this line, this one. So you're going to compute the next state, S prime. And then you're going to check if the movement is valid, the movement of the agent. Remember, you're trying to check transitions. So you have this if, and you're trying to check if like if the agent is like making the right decision, the right move, the right actions. And if it's making the right action, you allow it, like it moves into a like maybe up or down, makes an action through transitioning. Next, else, if the state is like still the same and all that stuff, then it's going to like stay in place. So yeah, there's more to the implementation, but those are the most important two parts, because you have to start with the environment, and then you have to also consider the transitions that the agent is going to make. So that brings us to the end of our presentation. That's it for inverse reinforcement learning. Thank you.